Привет, привет, Миша.
So we still have 2 minutes. Let's just wait. Maybe Nikita can start speaking about some general stuff. So, okay, it's a great pleasure to introduce Nikita Kalinin from Gwangju Technion Israel Institute of Technology, my dear friend and collaborator who is going to give us 3 lectures about his discoveries and around number theory and maybe a little bit of tropical geometry, quadratic forms, and things like that. So I think you may start.
Well, I,
Um,
I can start in 1 minute because officially it's still 1 minute till 9 p.m. here.
so I'm trying to speak about string theory.
Well, not today, but maybe next time or like on the third lecture, I can speak about string theory, right? Do you want me to speak about string theory?
Well, I'm very interested in this year's uh,
Well, I,
or
I,
other.
I I may try. We will see.
Okay, so it's 16 in Sofia, so you can start.
Okay, so thank you very much for invitation. So I'm very happy to speak in Sofia. And I hope one day I can speak there like in person, not just online. Uh, and that's a geometry seminar. So my talk is deeply related to geometry. And indeed, I consider it as a, I don't know, geometric story, not number theory. So number theory is kind of when you write geometry in formulas, but as the essence is purely geometric. And today I want to introduce the topic and topographs. And today should be very elementary, I hope. I will switch between two windows. So on one window I have a presentation, on another window I can write something. So if you have any questions, just ask me and I will stop and draw pictures, write formulas, and so on. Okay, so let's start. So the starting point for me and for this lecture, for me in this topic, is the following formula. So I discovered this formula like 1 year ago. And then I learned that it's not new and there are many proofs and so on. But somehow, starting from that, I got interested in number theory. So, okay, so what is the formula? So let's consider the set A. That's the set of questions. Just some sound.
Sounds.
Okay. So let's consider the set A, and this is a set of pairs of vectors in the first quadrant. So the both coordinates are non-negative and integer, such that these two vectors, they span a parallelogram of oriented area 1. Okay, so I write that as determinant of the matrix composed of x and y is 1. And so just consider this set of parallelograms. And then to each such a parallelogram, I associate a number. And this number is just 1 divided by the length of the first side times length of the second side times the diagonal, and all of them squares. And miraculously, if you consider this sum, it will be equal to pi over 4. So that's the theorem here, that 4 times the sum is pi. And I like very much formulas with pi. So that's my favorite formulas in number theory because pi has clear geometric meaning. And actually one of the proofs, it will count certain areas. And it will be a kind of just counting of areas. And I will give several proofs of this statement. And I hope that some of you also can find another proofs because like more proofs we have, it's more connections, it's very inspiring. So the goal of this lecture is to interpret this formula in several contexts. So one of the contexts Misha just mentioned is, for example, string theory. string theorists, they also have this formula, and it means something for them. And also, I want to reveal the connections to, say, the study of quadratic forms, the class number formula, and so on. Okay, so that's the topic. Any questions about the formula? Because kind of that's the main part. Okay, no questions. So let's now consider.
Sorry, what type of model are you use here? Is it a L2 norma, just standard Euclidean norma?
Yeah,
or
that's
kind
just
of
as, yes. So x square is just the sum of the squares of coordinates of x. So for example, if x is a vector AB, then x square just a square plus b square. But that's a very good question, because actually we can use another norms. It's also possible, and we will have not pi sometimes, but something very close to it. So indeed, so if you choose another norm, for example, you can choose another quadratic form. So quadratic form, it's a vector and gives you a number. And so here the quadratic form is just the square of the length. But you may use other quadratic forms. And that's kind of very important applications and modifications.
Okay, thank you very much.
Okay, so let's start with topographs. So a topograph, it's a certain planar connected three-valent tree, and that's it. It will be infinite, clearly. And topograph consists of such a tree with labels on vertices, edges, and regions. So the first definition is follows. So let's consider just labels on the regions. Like on the left, we have the labels R, S, T, U. And labels must satisfy the relation. Let me try to write here something. No, I cannot write. Or maybe I can. Yeah. Right. Okay, so that's the relation these labels must satisfy. So for every edge, I look at the four regions which are close to this edge, and I must have this condition. And if I have such labels, then this thing is called a topograph. Okay. Now, so what to do next? So let's see that if we have such a relation, it's equivalent to say that the numbers R, S plus T and U form an arithmetic progression, right? Because like the sum of R plus U is just twice the middle one. And if you have such a progression, it's natural to consider its difference. So the difference is just S plus T minus R, or that's the same as U minus S plus T. And we can write this number G on the edge, right? And so to do that, we just need to know the labels near a vertex. So you have a vertex, we have three labels, and then we can label every edge. So here also I want to orient every edge. I choose orientation such that the label on the edge is non-negative. Okay, because well, if it's zero, I can choose arbitrary orientation, but if it's like positive or negative, I can just choose the orientation such that if I consider the arithmetic progression in this direction, the difference will be non-negative. Then we have relations. For example, E plus G is 2T. So here it's E, here is G. And if you just look at this relation for G, and the same for E, if you just take a sum, then it will be T. So why I need that? Because you see, so it's clear that to specify the whole topograph, it's enough to specify just the vertex and three regions near such vertex. So if on this picture I choose R, S, and T, some numbers, then using this arithmetic progression rule, I can extend the numbers on all the regions. And what I just explained now is that it's enough to specify labels on vertices. So it's just the same. You can specify labels on three regions, or you can specify labels on three edges. So that specifies the full topograph. Now, just to get used to this notation, now let's consider one invariant, which is called discriminant. So it's D. It's minus EF minus FG minus EG. And I claim that it's the same for all the vertices. So you just take vertex, you orient edges outside. So with this orientation, some labels EF and G may be negative for now. And so I consider such a expression. And I claim that it's the same for all the vertices. And it's called the discriminant of the topograph. And I'm going to prove it. So I think it's this statement must be proven. Okay, so how to prove it? Let's look on the picture here on the right, on C. And I claim that it's enough just to look there. Okay, how to erase it? Like that. So you see, so here my orientation of E and G is like that. Right? So let's remember this statement that E plus G is to T. T is a region here. So it means that G minus E, that's how I draw them on this picture. G minus E is to T. And that's the same as I minus G, right? Because it's again just 2 times the label on this region. So I have this, and similarly, I have that G minus F is equal to H minus G. So it's here, G minus F equals to H minus G. So they're just the same identities here. And so when I multiply them, I have this identity here, then I just cancel G square. And now I just need to understand the signs. So now let me erase all this stuff. Now let's look at the signs here. Okay, so I see. So here I have minus EG, for example, this one. But this E is oriented towards the vertex. So actually it should be like when I change the orientation of the sign of the edge to be like here, it will become plus EG in this notation. So the same about GF. So I have GF. So G is F is oriented in the wrong direction. So I should change the sign. So I here have plus GF. And for E and F, both of them oriented in wrong direction. So when I change the sign, it will be just plus EF. And the same is here. So if I just change the signs such that the notation is on the picture B, it will be IH plus EG plus HG. And so that's, you see, that's exactly that. I proved the invariance of this invariant, well, of this D for 2 neighboring vertices. Okay, now if you understand it, I think you know everything about topographs, and then all the other statements about topographs you can prove like immediately. So you just need like this one formula here, and that's it. Any questions?
So you never said what are the labels. So do they belong to some field or maybe they're original things?
Can you speak slower because somehow I mean there is echo.
So the labels, they are just formal symbols or they belong to some numbers?
Okay, you might think about that the labels are just from some abelian group, right? Because we multiply them, you know, to define the discriminant, and we just add them. So just to define the topograph, you need them to be from just abelian group. If you want to multiply them, well, it's a ring. But in most applications, they're just integers or real numbers. Okay. Okay, now how it's all related to quadratic forms. Now let's do the following. So let's consider two vectors in Z2. For example, it may be bases. It will be bases, but for this slide, actually, we can consider any two integer vectors, or just any two vectors. So if I have two vectors, I can put the following labels on the topograph. So here I put the square of the length of E1, square of the length of E2, the length, square of the length of the difference, and here the square of the length of their sum. So like formally it's S, T, R, and U. And then, as you all know, there is a so-called parallelogram law. Is that if you have a parallelogram like that, then you can take the sum of the squares of diagonals, and then just sum of the squares of all the sides. That's a simple corollary of the cosine theorem. You just express diagonal via the like two sides and cosine of the angle, and since these two angles they just complementary, you can prove this relation. And you see, so if you just put this these labels near an edge, then near this edge we have this condition of topograph. And just one more remark that you can do the same with any bilinear form. So if you have bilinear form bxy, then you just form a quadratic form out of it, and then you have this kind of condition for any two vectors. And that's a simple corollary of just, you just rewrite this using this bxy, and then all the terms cancel. So in a sense, you have this cosine theorem not only for the usual lengths, but for any quadratic form. Any questions here? Okay, if not, then now let's introduce this topograph from another perspective. That's another definition of a topograph. We consider a graph such that all of its vertices are marked by superbases. Superbase is just the three vectors, E1, E2, and 3 in Z2, such that their sum is 0, and any two of them form a basis of Z2. And we consider such triples up to sign. So it means that the triple E1, E2, E3 is just the same as the triple minus E1 minus E2 minus E3. Okay, and then if you have a superbase, it contains three bases, like E1, E2, E2, E3, or E1, E3. And edges of this graph, they correspond to bases. So every vertex has three edges. And clearly, if you have any base, so you have E1, E2, that's a base, then you can complete it to a superbase in two ways. You can add here E1 plus E2 with minus, right? Or you can add here E1 minus E2, and here you write E2 minus E1. Right, so also we consider like vectors only up to sign. So here that's the picture. So regions for the topograph, they correspond to primitive vectors. Edges of the topograph, they correspond to bases made of such two primitive vectors. And vertices, they correspond to the superbases. Okay, and now I can do it for all superbases and all bases of Z2. So I have this huge graph. I just draw it on the plane. That's a planar graph. And then how to get labels in the previous definition. Just take any quadratic form, Q of X, and then just write Q of EI on every region labeled by EI. Right, and then immediately you will have this property of the topograph as we discussed just above. Right, so here you have like E1, E2, E1 plus E2, E1 minus E2, and then I compute F of all of them, well, Q. And as I just discussed, immediately I have this property of arithmetic progression. Well, now what I put on the edges? On edges, the labels actually the bilinear form computed at the corresponding basis. Again, that's just a simple corollary of the following fact. So if I put just squares of the length of vectors, then this difference of arithmetic progression. So you remember, so what was that? That was S plus T minus R, right? So this plus this minus this. So in this notation, it will be X plus Y minus X plus Y. It's just twice the scalar product. And if you write the same statement for any quadratic form, it will be just this bilinear form on the right. And since the labels are positive, so here I put the absolute value. Okay, and also since B is bilinear, if I change the sign of just one of the vectors, it just changes the sign. So it's correctly defined. It's well defined. Okay, now just some pictures. So here's the picture how to draw the topograph. That's a picture from the Conway's book, The Essential Quadratic Form. It's a very nice book. And the topographs are just a very small part of it. So how to draw a topograph? Just start with any basis. For example, the standard basis. E1 is just 1, 0. E2 is 0, 1. Oh, actually, maybe not a basis, just two letters, E1 and E2 symbols. Then you have a vertex, and here you write E1 plus E2. And on the left, you write E1 minus E2. And then you do just the same for every edge. So here for this edge, I have two vectors, E1 and this one. On the right, I write their sum. On the left, I already have their difference. And then you continue. So it's kind of just a branching tree. At every vertex, it branches in two directions. Okay, and then once you have such a picture, you just apply quadratic form to it, and you have a topograph with numbers on the regions. But for now, as also Misha asked me, so what can be the labels? So here the labels are just the vectors, the primitive vectors. I can add them, but I cannot multiply them. So I cannot define the discriminant for such picture. But once I change them to numbers by quadratic form, I can define a discriminant.
Well, I kind of disagree. You can formally multiply them. You can take symmetric thing or exterior product.
Yeah.
So it would be just interesting to know what is discriminant in this.
But well, you see, just so how you multiply them, you just have this E1 times E2 is basically kind of the definition of what is B of E1, E2. So you may think that it's a definition of this thing. Well, I mean, I don't know. Maybe it's interesting just to multiply them formally in this like tensor product algebra. Okay, so how to use topographs? I just tell briefly, just 2 seconds about that. Assume that we have a topograph as I have on the figure A. So I have some numbers. So that's our values of certain quadratic form. And then if this form is positive definite, actually you can prove that always there exists one vertex such that all three edges are outgoing. And so this vertex is called the well. So it's for positive definite quadratic forms, there is a unique well. And so you may classify positive definite quadratic forms by their wells. So you have a well and you have three numbers here. And then as you remember, it fully determines your topograph. And then different quadratic forms, they have different neighbors of their well. For example, there is so-called Selling's formula, which is very nice. So if you have such a vertex such that all three edges are outgoing, as here on the picture. So let's look at the labels on these edges. And so if all these three labels are positive, well, non-negative, so it means that they're outgoing, then you can express your formula in the following way. So just here you have the vectors E1, E2, E3. And then if you apply the formula F, well, that's your quadratic form. That's F of E1. If you apply it to the sum of these three vectors with coefficients, then actually it can be expressed using the labels here, alpha, beta, and gamma. And if alpha, beta, and gamma are non-negative, that allows you to find the minimal values of your quadratic form on integer vectors. Right? Because, for example, here, if you plug, for example, M1 is 1 and M2, M3 are zeros, then the value of F is just beta plus gamma. Right? And you see that it's not possible to get value less than beta plus gamma, alpha plus gamma, or alpha plus beta. And actually, these three values are the minimal possible values. So here it's kind of alpha plus beta, beta plus gamma, and gamma plus alpha. Again, you remember that in this way, we can recover the values on the regions from the values on the edges. So that's how to use them. And then you can develop huge machinery about that. And topographs are good because, in a sense, you do nothing new. But instead of formulas, you draw pictures. So instead of, for example, reducing the quadratic form to this minimal reduced presentation, you just walk over the topographs. So that's just a very nice geometric tool to, draw pictures instead of formulas. Okay, any questions about topographs? Because I finished.
So I heard the term river. So what is the river in this picture?
Here there is no river. So river appears only for non-definite quadratic forms. So for example, if you have certain values which are positive and certain values which are negative, then the region, the edges which separates positive from negative, it's called a river. And then, the classification of all the topographs looks as follows. So if your form is positive definite, well, the same as negative definite, it has one well, and the form is classified by the well. If your form is non-definite, but does not assume the value 0, then there is a periodic river with some period. And if your form assume 0, then there are like two lakes with the values are 0 and some like part of the river between them. Or maybe your form is something like x squared, then again, so you have one lake and certain branches out of it. So the classification of all the quadratic forms looks very simple when you speak about topographs. Questions? Comments? Okay, then let's go to the identity from the very beginning, and I will show you how to connect it to topographs. Because again, when you look at the proofs from the point of view of topographs, they're simple. So you remember that we have identity. So the identity is as following. So you consider all the possible parallelograms of the oriented area 1. So here it's like A, B, C, D, and you have the condition that AD minus BC is 1. That this determinant. And I want to show that 2 times this sum is pi over 2. And so the proof that I found, that's how I discovered this identity. I wanted to telescope something to get something reasonable. And I explain what I wanted to telescope. So I wanted to telescope in the following sense. So if you have function f defined on vectors, on a pair of vectors. So for example, in this case, it will be just the following. So I take the scalar product of x and y, and I divide by the, well, so here it's x squared times y squared. Divide by the squares of the lengths. And then if I have two vectors, I can consider the following expression. That's f of xy minus f of x plus yy minus f of x plus y. So this corresponds to the following. I have expression for this parallelogram, and I subtract the expression for such a parallelogram and for such a parallelogram. Right, and then I start from the parallelogram of kind of standard basis. That will be f of 1, 0, 0, 1. Then I subtract these parallelograms, and they generate more parallelograms and so on. And when I just take a sum of all such expressions, then all these terms will cancel, right? Because if I do it for the first thing, so here I will have this f of y minus this parallelogram and minus this parallelogram. But then I will subtract them. So I will add this f of this minus f of this minus f of this plus f of this minus f of this, and so on. And so the terms will cancel. Okay, now what I want to do, so let me erase all that. So the expression here, f of xy minus f of x plus yy and so on, if you just look at it and compute it, then it will be equal to the following. Just minus 2 determinant of xy squared divided by like x squared, y squared, x plus y squared. So that's true for any two vectors x and y. And in our case, the determinant of xy is 1. Right? And then when I apply this procedure, the determinant always will be 1. Right? Because if determinant of xy is 1, then the determinant of the x plus y and y and x plus y is also 1. So it means that when I take sum of these things on the left, on the right, I will have exactly minus 2 times this. And all intermediate terms, they cancel. Now to finish the proof, you just need to carefully estimate what's left. So first of all, for sure, what's left, that's the vector, well, f of 1, 0, 0, 1. That's kind of the starting, the first term here. But this is 0, right? Because here I have scalar product. And so initially it seems that like all terms canceled. So the first term is not canceled, but it's 0, and all other intermediate terms, they cancel each other. But that's not quite true, because you have some contribution from infinity, from the boundary. How to do it formally? So let's do the following. So let's consider the sum of this thing over an. So here an, that's all the vectors such that both of their coordinates are less than n. Well, not bigger than n. And so I do it for all xy such that x and y from an. So all the internal terms, they cancel, only the like boundary terms leave. So what is the boundary? That such two vectors from an such that x plus y is not from an. Then I have such terms. And this sum turns to pi over 2 minus. Now let me draw the picture, why it's true. So what is the procedure? The procedure was as follows. So I started with two vectors like that. Then I added one more vector. And now instead of one parallelogram like that, I have two parallelograms. Okay. Then again, so for each of them, I cancel this parallelogram and instead add two more parallelograms here and here. So basically, it means that on every step, what I have, I just kill this parallelogram, and instead I add one vector here, the diagonal, and now I have two parallelograms. So it means that when I consider this stage AN, how to draw it? So basically, I just take all the vectors here, all the primitive vectors here, and then all my parallelograms are just parallelograms with such sides. And I want to understand the contribution of all of them. But now what I compute actually? I compute, as you remember, if I have x and y, I compute x times y divided by x squared, y squared. And I claim that it's approximately the alpha, where alpha is just the angle between x and y. And then it means that the sum of all such terms is just equal to the pi over 2. Okay, why this is true? Okay, first of all, if x and y, like if at least one of them is big, then x times y is approximately x times y. So the fraction is just cosine. So the thing is just cosine alpha divided by xy. Now let's remember that all the areas of the parallelograms is just 1. So I know that xy times sine alpha is 1. So actually it means that sine alpha is just 1 divided by xy. So here it means that this thing is just cosine alpha sine alpha. And that's just 1/2 of sine to alpha. And that's approximately alpha. Right? So plus certain terms of lower order, but when you subdivide pi over 2 into small parts, and then you take just this part alpha plus something of smaller magnitude, then you take a sum, all these small parts, the sum tends to 0. So it means that the sum of these things is approximately pi over 2, and in the limit is just pi over 2. So this total angle here. Okay, that's what I wrote here. So the sum of these things tends to minus pi over 2. Since the area of the parallelogram spanned by x and y is 1, so this term, the scalar product divided by squares, is just the angle between x and y up to second order terms. And this set of angles partition the angle pi over 2. And so that's why here on the right, you have exactly pi over 2. Questions? That was the hardest part today, kind of the only real proof. Okay, now let's derive corollaries and interpretations. So what is a topograph interpretation? So as you remember, so what is this set A where we take the sum? So you remember you take this like the vectors 1, 0, 0, 1, then another parallelogram and so on. That's exactly what I have here on this picture. Right? So I just started from 0, 1 and 1, 0 and take this part of the topograph. So every vertex here corresponds to a parallelogram of oriented area 1. Right, so that's exactly, so the first parallelogram is just E1, E2, and that's the diagonal. Then here I have the second parallelogram, this and this is that diagonal, and so on. So basically, and their lengths, that's exactly the labels on these regions. So as you remember, later here we put the length of E1 square, the length of E1 plus E2 square, and so on. If our quadratic form is just this like x squared plus y squared, the sum of the squares of the coordinates. So it means that in terms of topographs, this summation is nothing else, just the sum over r square, s square, t square over all the vertices in this part of the topograph. Now, how to interpret this telescoping method in terms of topograph? Okay, we just present every value like that as a sum of terms corresponding to 3 incoming edges. Right? So for every edge, we have this function f. Remember, f of xy is just x times y divided by x squared y squared. And up to science, it's exactly this. And then, so you have a topograph, and then for every edge, here you have 3 terms. But then when you take the neighboring vertices, so here and here, for this vertex, this edge will come with different orientation. So we just need to check that the function which we associate to every edge, it changes sign when we change the direction of the edge. And then all the intermediate terms, they will cancel. So when you take the sum over such a big part of the topograph, so the remaining part will be just the function f, the sum of the function of f for the edges kind of crossing the boundary. And that's exactly what happens. So here I just need to say that if I have a edge, the edge corresponds to the basis E1, E2, and my function f is just like that. And if I orient my edge with opposite orientation, it corresponds to E1 minus E2. And this thing is antisymmetric. So it's minus f of E1 minus E2. So it means that you can consider more sums like that. So you just have a topograph, then you define a function for every edge with this property. And then you just telescope of the whole topograph. If you can control what happens at infinity, then you have a nice identity. Something like sum of this one or divided by this is equal to something. So this will be the topic of the next lectures. So today we consider only this. Yeah, and actually here it's not squares, just 1 divided by RST, right? Yeah. So not squares. Okay. Just maybe 2 more slides, and that will be everything. Okay, so that as I think Denise asked me, so what happens if you consider not the standard norm, but something different? So for example, you can say, what if I say that the length of the vector AB is not a squared plus b squared, but this like q of AB is just a squared plus 2b squared. So what if I do this? So I want to find the sum of this expression again for all the parallelograms of the oriented area 1. So what to do? Well, for example, you can just consider them as vectors, not these vectors as kind of the integer vectors, but instead these kind of vectors. Then their length is exactly this one, like in terms of A and B. And then I can write the same statement, so the same expression for f, just all the same. But here instead I will have, you remember this 2 times the determinant square, and now the determinant will be square root of 2. Because the area of the fundamental parallelogram for such a lattice is just square root of 2. And also you remember, so in this estimate, when I estimate, so what happens at infinity, I said that 1 divided by xy is just sine alpha, because the area of the parallelogram is 1. But now the area of the parallelogram is not 1. So it means that, so here also I must divide by the area here. So it means that the contribution at infinity will be not pi over 2, but pi over 2 divided by square root of 2. And so if you just replace all these things, so what you have the following. So if you plug here not 2 but by t square, then the contribution of the angle will be pi over 2 divided by t, right? By this kind of, you see this kind of t square is equals to 2. Right? And so also I have to divide by the discriminant, determinant square. So here I have minus 2 times determinant square, so it goes to the denominator here. And so if you plug here t equals 1, you have exactly pi over 4. Right? It's just our initial form here. It's like pi over 4. But for general t, you have this thing. Okay, now I can ask, okay, what happens if I plug here t equals to 0, for example? Well, I cannot do t equals to 0 because, well, on the right I have infinity, and on the left also it will be infinity. Or maybe I want to have here not a square plus b square, but a square minus b square. Maybe I want to plug here t equals I. So can I do that? Well, in a sense I can. But what I need to do? So why I cannot plug here t equals to 0? Because here there are vectors, for example, AB equals 1, 0, and CD equals 0, 1. So if I plug here t equals to 0, then this c square becomes 0. Right? And so I divide by 0. That's why the sum diverges. Or the same, for example, if I have the vector here AB equals to 1, and if I plug here t equals I here, then it will be 0. So what to do with that? I can just restrict the range of summation. So instead of the whole kind of the half of the topograph, I can go to some branch of it such that I have no zeros in denominator. Okay, so what happens if I do this? So let's consider this the sum of all these vectors such that they are from the cone generated by these two vectors. So I have 1, 0, I have 1 t, and I consider their sum of their sum, and so on. So I just generate this thing by two vectors. Then I can just repeat all the same statements, except that, so first of all, the whole angle will be not pi over 2, but the whole angle will be arctangents of t, right? Because, if you have two vectors here, 1, 0, and 1 t, then this angle, that's arctan of t. Because, well, so here just t. And the first term will be different. So you remember, the first term is just f applied to the first two vectors, which generate the whole thing. So previously, the first two vectors were orthogonal. So the first term will just 0. But now I should like multiply here and divide by the product of their lengths square. So now it will be not 0, but 1 divided by 1 plus t squared. Well, and so when you just do this change, you have the following formula, which now works for any two vectors. Oh, I cannot write. Oh, this one. And now I can look what happens for t equals to 0. So let's look carefully. So when t equals to 0, I just need to look at the first expansion, the Taylor expansion, the first term in the Taylor expansion. So on the right, I have arctan of t divided by t. What is this? This is just like 1 minus t squared over 3 plus t power 4 over 5, and so on, right? So here is just 1 divided by 1 plus t square. It will be just 1 minus t square, and so on. So we don't care. So these ones, they cancel each other. And then I have a term corresponding to t square. So here it will come with plus. Here it will come with minus. So it will be like 2/3 t square. And then I divide it by 2t square. And so I just have 1/3. And so it means that if I just plug t equals to 0 here, I have the following formula. And this formula has many proofs. It's like Mordor-Turnheim series. And well, so this gives you another proof of this simple formula. Maybe also next time I can tell you about geometric interpretation of this formula, because it's just certain area under parabola. So it's just the way to compute the areas a la Archimedes. Okay, what if I plug I? Well, you know, when you try to compute arctan of I, it's a problem. It's not defined because it's divergent. So when you plug here I, so here these terms will diverge. That's bad. But I can plug there I over 2, and then it converges. So what happens in this case? Well, you plug here I over 2. So this becomes minus b squared divided by 4. So I just multiply it by 4 here. And so this 4 gives you 64 here. Now the tricky part. So this 1 divided by 1 plus I over 2 square, that's this. And the more interesting thing is that arctan of I over 2 is just logarithm of 3. Well, multiplied by I over 2. So you can compute arctan of complex numbers. Well, so this gives you this formula. And so here you take a summation over all A, B, C, D, such that the determinant is 1, and A is bigger than B, and C bigger than D. And then, you know, no terms here are kind of are zeros. Or what else can you do? You can look at the formula above, the formula with T, you know, this formula. And then you can just expand it in C, right? You just say that here you have 1 divided by, well, a squared times 1 plus t squared, b squared over a squared. And then just 1 over a squared, and then you develop it like 1 minus t squared, b squared over a squared, and so on. Right? So you can do it. And then you can just look at the coefficients behind powers of t. That gives you the values of the sums like that, like this one. Well, so when k, n, and m are zeros, so here you have just 1 divided by a square, c square, a plus c square. But when k and m are bigger, then you put b square in numerator and a square in the denominator. And so, and the same with other things. I don't know why these sums are useful. It's just very, very nice, I think. I just like them. Any questions about this part? So basically that's the whole content of today's talk. I have just one more slide, which has no connection to this.
What about upper bound of generalization in this case? You show that we can consider almost all formula like a square, I know, 1 sine t b square, just maybe plus, maybe minus. But what about other norms? Is this one, but what about the whole picture of norms that this instrument can be solved?
Well, you can define them, but I don't know how to compute them. You see, so why all these things works perfectly? Because the same telescopic summation works. So because on the topograph, when you want to consider a sum of like 1 over RST, you can just define something in terms of bilinear like form here, because like here E1 times E2 is just bilinear form of E1, E2. And then everything cancels and everything is good. But if you have just another form which doesn't come from well, another norm which comes not from a quadratic form, then I don't know what to put on the edges to make telescopic works. Because here you see this is how I found such a formula. So first I put something which telescopes, and then like you try different things. You try different things for f, such that this like sum of well, so you try different things for f, such that
Isn't it possible for cubic forms, a three-dimensional topograph good work or something like that?
well, I don't know. I mean, you can also write the same. I think you can also write the same like telescopic things.
Yeah, but because there are now more terms, it seems that you need more space, like this three-dimensional space with more regions.
Yeah, actually, also I don't know much about topographs for 3 dimensions because this kind of branching process may be defined differently. It's not like you have like all possible super bases. No, there
That's
is
right.
no
That's
canonical
right.
generalization. And so once you define the procedure how to generate certain vectors, so here just add the sum. Like I start with xy, add x plus y, x plus y, add their sum, and so on. In 3 dimensions, it's not like that. So there are like different topographs, and formally surely it's possible. Just take any graph, write something on edges, and like such that it depends on the orientation, like it's anti-symmetric. And then you immediately have telescopic something. But to make it somehow canonical or like related to other subjects, I don't know. Because like next lecture, I explain how this all related to class number formula, maybe to string theory and so on. So this kind of sums, they're considered in other places. But what to do with cubic form? Well, actually in string theory, they also have it for cubic form, right? So in fact, they have it. So they have something like 1 divided by x square, y square, z square, and here x plus y plus z. So maybe your question is that, well, simple. Maybe indeed this is all already done in string theory. Okay, so then I present you the last slide. And the last slide is a geometric way to prove this formula. Actually, it's due to Hurwitz. It's 1905. It's more than 100 years ago. And then when I discovered this formula, I asked the question on matter of law, and David Speyer, he also answered this question, and in the same way as Hurwitz did, actually. And the Hurwitz proof was the following. So that's article of Hurwitz about class number for quadratic form. And well, somewhere in the middle, he computes this kind of sums by the following way. So let's consider the unit circle and parameterize the right half of it, well, by standard parameterization. Right? So here goes the point 1, 0. Here the goes to point 0, 1. Here it's 1, 1. Well, and so on. And then you can consider a triangle associated to vectors a, b, and a plus b. Well, x, y, x plus y. Okay, so for example, this triangle. And then this triangle. It's 2, 1. Or this triangle. It's like 1, 2. And by direct computation, you just see that the area of such triangle is actually equal to, to this. So it's just twice the sum we consider. And then you see the sum of the areas of all such triangles, that's exactly pi over 2. And each triangle just twice my term. So it means that the sum that I consider is just pi over 4. And the other summations can be also interpreted in this way. So instead of a circle, you have an ellipse or a hyperbola. And then you just look some triangles and compute the areas. So for example, for parabola, you've got, this. Okay, that's all for today.
Thank you very much.
Thank you.
So just a question. So as far as I understand, this formula for parabola that you mentioned, the triangles are exactly same as in this relation to, let's say, caustics.
No, in
Or
fact, well, I will speak about that the next time, because if you have a curve, then you may form two kinds of triangles. So you can have triangles inside of the curve, or you can have triangles outside of the curve. So kind of you can carve triangles inside by adding more and more sides, or you can cut triangles from outside. So not carving, but like kind of the other way of like when you work with stone. And so this kind of triangles, they give the same formula for parabola, because parabola is kind of self-dual from this point of view of this like Legendre duality. But for other curves, it's different sums. And for the circle, it's not the same sums. So for parabola, it doesn't matter what kind of triangles you take, inside or outside. They give the same formula.
okay, I guess there are no more questions. Thanks a lot for this elementary introduction. Yeah, I hope to hear more things next time. Well, it was really, yeah, it was very instructive. Thank you.
Thank you very much for inviting me.
Bye now.